Okay, so we'll do, in this lecture, we'll do two questions where we have some data and we fit a curve to the data. That then is a mathematical model, and we'll ask some questions about that. Now, you will see references to like Winter 2018, which was an exam paper, of course, but you won't have exam papers. It'll all be continuous assessment. So basically, your continuous assessment will be similar tasks, but open book over a number of weeks, using Excel as well. Okay, so here's a thing we have. An engineer was tasked with finding the maximum deflection due to a symmetric load on a beam of span 5 meters. So this is what we got. She did not have a formula for the load per unit length at each point. So she only has data, she doesn't have a formula for this. So instead decided to make some measurements of distance from one end of the beam, x, and of the load at that point, and fit a curve to the measurements. So what she's doing is she's going to basically get a formula for the load per unit length, and then she can do what we're going to do in chapter 2, which is basically do some maths to solve the differential equation to tell herself what's the bending moment at every point, what's the deflection at every point. In particular, she's interested in the maximum deflection. So she'll find where the derivative of the deflection is equal to 0. Okay, so she decided that the curve resembled an N-shaped parabola, so decided to fit a curve of this form. Now this was one we saw, so this is one that's equal to 0 at 0. Now the A is going to probably almost certainly come out as negative. That's what we're going to want to hope to see. So let's see the data. She has made 10 measurements at 50 centimeters along the beam, and she's measured the load per unit length at each point. Now I'm not sure exactly how that would be done. It's probably done in such a way that the load is proportional to the height of the load. I don't actually know. Obviously I made up this problem. How realistic it is a different question. But anyway, here's our measurements. It looks fairly symmetric. 15.3, 15.2, 20, 20, 22.9, 22.8. It's actually very symmetric. So, and this thing is, parabolas, by the way, are symmetric through what might be called their central axis. So there is a symmetry in parabolas. So we can see this. Now it's not exactly right, but that's what you'd expect because the measurements aren't perfect and maybe the design of the load isn't perfect. There's lots of things going on. So what's question A? By fitting w equal to ax squared plus bx to this data, find the best values of the constants a and b in the least squares sense. So what we have to do is find the normal equations for this. It says use at least 3 significant figures. We'll probably go to 4. Now there's a hint where lots of the calculations have actually already been done. Adding up the wx is this, adding up the x cubed is this, etc. In your assessment, you will not be given these hints. You will have to calculate these numbers yourself, probably using Microsoft Excel. Okay, so our first job anyway, certainly here, is the curve of best fit in the least square sense is found by solving the normal equations. So we have to find the normal equations here. So let's see what we have on the next page. So I'm going to write up what we have at the top. We're asked to fit W, now this is like our y, equal to ax squared plus bx. So what we want to probably identify here is the multipliers. So the multiplier of a is equal to, what's multiplying ax squared? So it'll always be the multiplier of the constants that you're looking for. And we're looking for a and b. And the multiplier of b is x. So our job here is to write down these normal equations. So let's go. Multiply everything by x squared here. So I'll get wx squared, add up, equal to. Now ax squared by x squared by x squared is x to the 4. So I get ax to the 4, add up. But the a is a constant that can be taken out. So a times add up x to the 4. And then x squared times bx will give us bx cubed, and take out the constant b. And add up. So that's the first one. And now you don't go back to this, you go back to the original here to find the second one. And the other one, the multiplier of b is x, so multiply everything by x and add up. W times x is wx, and add up, equal to, take out the constant a. Now x squared times x is x cubed, and add up, take out the constant b, and x by x is x squared, and add up. So this is what we get. Now typically what you'd have to do here is you'd have to make a table. So I'm just, okay, so if we look at the data here that we have, we've only got x's and w's, but we need to find w by x squared and add them up. Also x to the 4, also x cubed, also x squared, and also wx. So what I'd probably do is I'd table x squared, then I do w by x squared, I'd probably square x squared, and I'd do x by x squared, or I'd just do x cubed, and I'd also do w by x. I think that'd be everything, and I add them up. So as I said, in an assessment, you'll actually be doing that in Microsoft Excel. In an exam situation with this many data points, I'll actually give you these numbers. So in this particular one, I'm going to write down now what I'm going to do is I'm going to write them down. I'm going to do multiple of a plus multiple of b equals constant. So let's do the first one here. I get, add up x to the 4 times a. Add up x to the 4 gives me 1583 times a. Plus, add up the x cubed times b. I look at the previous page and add up the x cubed gives me 378.1. You'll see later on I'll be quite fussy about rounding, but here everything is, there's errors involved, so you can't really be that accurate anyway, so little rounding errors are okay. Equal to, add up the wx squared, which is 1170. Okay. And the other equation, which I really actually want to write here because I want to kind of line them up, even if I'm doing Cramer's rule or not. So the other equation says a times add up the x cubed. The add up the x cubed is 378.1. Plus b times add up the x squared. The add up the x squared is 96.25. Equal to add up wx, which is 392.8. Now here I have nasty decimals, so I'd recommend using Cramer's rule. I think what I'm going to do though is the Cramer's rule, for example, says that a is equal to, and space is going to be a little bit difficult, I might have to kind of use some of this, dA divided by d. Yeah, definitely going to need some space. So dA, or what I can do is maybe write dA and then over d, and then hopefully record d with a little note. Okay, so what dA is it's the determinant of this matrix, so these numbers 1, 2, 3, 4, but the a coefficients replaced by the constants. That's what dA is. So I put this in 1170, 392.8, and then the other constants here, 378.1 and 96.25. Okay, divided by d, which is the determinant of this matrix here. And I want to record this for b. So this is just, there's no swapping in or out or anything, it's just 1583, 378.1, another 378.1. I'm just going to double check that. Do I get the same thing twice? Yeah, add up the x cubed twice. Yeah. Now at the end, like, the hope is that if there's some mistake made, usually we'll hope that our answer won't make sense. So I referenced earlier that the a should be negative. So if the a came out positive, I know I've made a little mistake somewhere. And of course you can make a mistake that doesn't quite show that, and you can be unlucky. So I think what I'm going to do is I'm just going to calculate this d here, because I'm going to use that for b as well. And I'll go to 4 significant figures. It just asks for at least 3. So right down diagonal, 1583 by 96.25 minus left hand diagonal 378.1 by itself, which means squared. So 4 significant figures, this comes out as 9404. I will be using that below. Now I'm going to do this thing here, which is 1170 by 96.25 minus 378.1 by 392.8 divided by answer, so what was stored in the calculator. And for significant figures, yeah, it's good. I'm getting something negative, minus 3.81. So do three figures, and then the last one is 8. Should it round up? No, because the next one is a 0. There's that. And now we'll do Cramer's rule for b. b is equal to db over d. And I already have b to 4 significant figures. I probably should go to 5 significant figures if I want this to correct to 4, but it's a bit dodgy there. But again, as I said, you don't want to round too harshly, but you can't get hung up on the rounding here because it's all kind of rough anyway. So let's just take this figure, 9404, and let's do dB. So dB is the same as this, but you replace the y, or in this case the b coefficients, with the constants. But the a stays the same, 1583. 378.1, and let's replace out those b's with these. 1170, 392.8. So I think what I'm going to do, I'm just going to put this on top and then divide it by 9404. So we get right down diagonal, 1583, that's what I mean, right down minus left down. 1583 by 392.8 minus 1170 by 378.1 divided by 9404 comes out as 19.0. And then the fourth significant figure, well, it's a 7, but it's 79, so I should round that up to 8. So I get a mathematical model, so it's good to put your answer together then. W is equal to A, which is minus 3.818 x squared, plus B, which is 19.08 times x. So this is our curve of best fit, and now we're going to answer some questions on it. So hence find the location of the maximum load. So looking back here, the maximum load is going to occur where? Well, it can't be at the maximum load. You can't have a positive slope because that means that the load is still going up. So you haven't reached the max. It can't be like this because then the maximum will be behind you. The slope has to be 0. And the slope here is the derivative of the load with respect to x. We want that equal to 0. That's how we find, and it's looking for the location, so it's looking for the x value, say x max there. So what we need to do is find where the derivative of the load per unit length with respect to x is 0. That will be the location of the maximum load. Right, so I want to solve the derivative of this equal to 0. So I get dw dx. Now something that we're going to see a bit later on, and I want us to get used to, is when you have a constant times a function, you fix the constant and differentiate. I know it's slightly different to something you've seen before, but I recommend that's what we do. So fix the constant, minus 3.818 times the derivative of x squared is 2x, plus fix the constant, 19.08 times the derivative of x is 1. And what we want is this to be equal to 0. A little notation I might show you that's nice is if you put an exclamation mark on the equals, it's like I want this to equal 0. There's different times and places that I'll use this. So we just have to solve this little equation for x. I think the easiest thing is maybe just get rid of this plus 19.08, and the inverse of adding that is taking it away. Do that to both sides. Now I have the 2 by the 3.818, I can do that here. So I get minus 7.636x is equal to minus 19.08, and the x is multiplied by this negative number. So if I want to undo the multiplying by the negative, I should divide by the negative. So divide both sides now by minus 7.636. So I end up with x is the location of the max. Let's just call it x max. That's nice. It's approximately, we'll go with 4 significant figures or whatever. 19.08 divided by 7.636. It's coming out as 4 significant figures, 2.49, and then the 8 should be rounded because it's 86. And the is there anything about units? We want to try and use units when we can because we're engineers. X is measured in meters, yeah. So 2.499. Okay, which is basically 2.5 meters. Now here's something. It says the load is supposed to be symmetric. Now a good question is, why isn't the measurements coming out as symmetric? Well, you know, we won't get into that, but you can imagine yourself why that could happen. Now the thing is, with a symmetric load, you're certainly expecting the maximum at the midpoint. Otherwise it isn't symmetric. So given that the load is symmetric, comment briefly on your answer. As expected, it is at the midpoint, well, to the nearest, I mean, this is 49 centimeters, 0.9, I mean, to the nearest millimeter. Is at the midpoint, well, to the nearest millimeter, which is basically at the midpoint. In other words, what you'd expect. Now, this would be, like, one of the things you have to get into your head for the assessments is that you're going to have a lot of time and you're going to have opportunities to correct your work. So if you, for example, get an answer here, say negative, which is clearly wrong, or something bigger than 5, it's not really going to be good enough for you just to say, oh, yeah, that's wrong. You're going to have to, you should fix it, okay? But this looks pretty good here. Right, next thing here, using the values of A and B found in part 1, estimate the total load. Now this kind of feeds into something that we'll see a bit more in the next chapter, but well, actually it isn't, to be honest with you, but this, I suppose the question is just given here. So this is the load per unit length. Now it's changing all the time, but essentially what this is doing is add up the load per unit length by a little bit of length. So this is adding up little bits of loads. You get the total load. Okay. I think when I asked this question last year, only one student completed this, but this is not a difficult integration question, but we'll do it. So we get, I don't have much space here, so we'll do, let's throw it in here, 0 to 5, a, well, minus 3.818 x squared plus 19.08 x dx. Okay, so hopefully you remember this very, very basic integration. Now again, if you're anti-differentiating, well, how do you integrate? You anti-differentiate, then top limit minus bottom limit. Again, I'm recommending that you fix constants and anti-differentiate. That's going to be relevant for the next section as well. So I'm going to fix, we do these square brackets, fix the constant minus 3.818. And the antiderivative of x squared, well, you can go into your tables. I mean, you can figure this stuff out. It's not going to be an exam situation. The antiderivative of x squared is x cubed over 3. Add 1 to the power, divide by the new power. We'll see this in the next chapter as well. Plus 19.08. And what about x? What's the antiderivative of x? Well, if you can't remember what it is, you can say that x is x to the 1. And so it'll be add 1 to the power x squared over 2. And we're going from 0 to 5. And now you do top limit minus bottom limit. So it'll be minus 3.818 divided by 3. Substituting the top limit, which is 5. That's to be cubed. Plus 19.08 over 2 divided by 2 times, so substitute in the 5 for the x, you get 5 squared, take away, now if you sub in the 0, 0 cubed is 0, and sub in the 0 here, the 0 squared is 0, so this is just actually ends up being 0. Now you have to be careful that this was cos of x, cos of 0 is not 0, or e to the x, e to the 0 is not 0, but here they are. And we'll bang this into the calculator, see what we get. Minus 3. Now again here, if you get something negative, that's suggesting that there's been some kind of a mistake. Plus 19.08 over 2 times 5 squared, which is 25. And it comes out to 4 significant figures, 79.4, and then it's 1/6, so I'll round that up. Now the load is measured in kilonewtons, not kilonewtons per meter. There's possibly a confusion between the notation WT and WX, because WX is kilonewtons per meter, whereas this is total load. Like, it's actually kilonewtons per meter times meter, which is kilonewtons. Okay.